Finally, the body axial drag. Here we do have the pressure term, and it's going to be really relevant in this case because, well, the rocket ends abruptly, not like a fin, in which the the boundary layer sticks to the fin, and we don't have pressure drag. It's not the case in the body. Fortunately, it's gonna be impossible for the airflow to stick to the surface, and it's gonna create a zone of suction, which will be the base drag term. Okay, so let's go. The axial drag of the body. Yeah, finally I am writing all the subscripts. Friction is this. Nothing strange here, just the length of the rocket, diameter, Mach number, dynamic pressure, everything international system. As you can see here, we do have dimensional terms, so just be careful. Just put this in meters and this in pascals, and you'll be fine. Then let's go actually with the wave drag. Okay. Alright, I just paused the video because, yeah, it's just me writing down this long equation. So, couple of comments. Mach number, arctangent. Wait, I put capital D for the diameter of the rocket everywhere, so I'm just gonna be consistent with my notation. Ln, you know from the previous section, the length of the nose, reference area. You have a new term here, the surface of the nose tip, and reference area, Mach over 0.2 minus 2. So the area of the nose tip, we define it as, well, the area referring to the diameter of the nose tip, and we define the diameter of the nose tip as this diameter. Well, the diameter of this curvature. So if we kill this pointy edge and we give the nose tip this slight curvature, which will ease a lot all the stresses on the tip. If we give it a small curvature, it's just the drag is going to be so the drag is going to be slightly higher if you round the nose, but it's going to alleviate all the mechanical stresses and also the heating, actually, because so it is desirable to give a small just a small curvature. I think a 10% is something typical, I believe. 10% of the diameter of the rocket, just like a rule of thumb. So yeah, as you can see here very clearly, sorry, no, I was talking about wave. Here, I'm talking about the body axial drag, including the nose, the boat tail, and all the sections. So yeah, take in mind that some parts can be, relative to the nose cone. Some parts just the boat tail. So So as you can see here, for example, the wave drag is mostly related to the length of the nose. As you can see here, the finest ratio between the length of the nose over the diameter of the rocket. If you remember, I called this the... No, I actually didn't. This was another variable, right? This was the specific length of the nose, but non-dimensionalized with the length of the rocket, if I remember correctly. Yeah, that was with the... Yeah. This is the finest ratio. This ratio here, but yeah, with the diameter. Sorry for messing up. So typical ratios for fineness ratio. Philemon called this fineness. This is the the main parameter here. As you can see, this parameter here is really low because the S of the node, this value here is low because the curvature you're gonna give it is pretty low. So this is a big term related to the wave drag, and inside here what we have, well, this is basically 1, close to 1. This is just Mach terms. Can't do much about it. Well, we can, but the geometry terms are here, and the geometry only depends on the fineness ratio. So, fineness ratio. Typical fineness ratios, high fineness is something like 5. So yeah, that's... But again, it's always a trade-off. You're going to have lower drag with a higher fineness, but you're going to have more mass, longer rocket. So, up to 5... Yeah, something typical. Higher than 5, kind of strange. Haven't seen that much, but yeah, it's your task to see what fineness ratio you give it. This is systems engineering, so there is no one best solution. I'm just giving you all the tools, and then it's your task to see what's the best for your rocket. So yeah, wave drag related to the body. It's all about the nose. Friction. It's all about the overall fineness ratio. This is the length of the rocket over the diameter of the rocket. So if we have a longer rocket, we're gonna have higher friction. Body friction. I think it's nice if you plot this with different parameters, so you can see, the influence of the Mach. How important is this? How important is that? It's always nice to, to chew these equations like I did before in section 2.2. These equations are much easier to chew, so I'll leave that up to you. I'm going to show you just a plot I did time ago. I just found on our Slack, so I'll show it to you later. But first, I have to finish with the base drag of the body. So the base drag is going to be, as you can imagine, the critical part is going to be the boat tail. If we have a boat tail here, where, well, we can reduce the suction area. So if we have a boat tail, well, the flux is going to be attached, and the suction will only appear here. And so that's why we put a boat tail, and that's why, any flying vehicles have their geometries like this. You can see it in airplanes and everywhere. So the base drag for the body is piecewise defined. So for Mach numbers below 1, we have this expression. We have a new variable here, which is the area of the boat tail, and K. gonna get into that in a moment. And for supersonic, well, we have this expression, this Mach number, reference area, K, and the area of the boat tail. The area of the boat tail is simply defined as you can imagine, and diameter of the boat tail is simply the diameter at which the boat tail ends. I think we may have talked about dB in stability, but we discarded it as the normal force on boat tails is low. So what is K? Well, K is just a constant, and it is piecewise defined as well. But instead of the Mach number, this is K, and depends on if we're in the powered phase. This is powered. We're in the powered phase of our flight, or the coast phase. Coast means that our rocket is not firing. So what does this mean? Well, if we have let me draw this larger, because there's a new variable here as well. Okay, so this is the end of our rocket. This is the nice boat tail. And then inside here we have a nozzle. It might go like something like this. Not very divergent, but... and the nozzle is firing. This is AE, the exit area of the nozzle. So what happens if we have a powered flight? Well, we have a jet here of high velocity gases. So the flow is going to do something like this. It's going to be attached to the boat tail, and then we have no low pressure zone, because we have the jet here. So we have way lower base drag. We only have maybe this part of suction. So our base drag is greatly reduced. Okay. Indeed, if we if our exit area of the nozzle were to be the exit diameter of the boat tail, we wouldn't even have this small low pressure zone. We would have zero base drag, because we would have no depression zone. So what happens in the coast flight? The coast phase of the flight, well, we have no jet here, and well, the flow is going to do something like this, and then we have a large depression zone here, low pressure zone, which will cause base drag. So if we had no boat tail, well, it would be larger. Then we have this term here. So yeah, the boat tail can reduce a lot. Oh yeah, but you can't put any angle here of boat tail. Call this boat tail angle. I don't know. Let's call it. We've used a lot of variables. Let's just call it boat tail angle. This boat tail angle, rule of thumb, it always has to be below 8 degrees. Okay, if you have higher than 8 degrees, the flow can it can disattach, and it can be worse. So if you want the flow to stick to the boat tail, you gotta choose really low angles, like 8, 6, 10 at most. If not, you're gonna get an even worse, an even worse effect that what you were trying to get in the first place with the boat tail. So yeah, that's a rule of thumb Fleeman suggests. Okay, you have a nice graph of the base drag at different Mach angles, at different boat tail angles at different Mach numbers. And you'll see that at high boat tail angles, I don't know, 15, 17, you actually have higher drag. So yeah, not desirable. So yeah, that's about all. I'm gonna show you a plot. So remember this this is when we had this problem in the simulator that it didn't make sense. The altitude it was achieving. So we messed up with the drag somewhere. I think it was with the fins, that there are some imperial units and stuff. I can't remember which one just went crazily high. But this is a very nice plot. You can see here that if we have geometry fixed, it's very nice that, well, actual drag only depends on Mach. Kind of. There is the dynamic pressure, which isn't quite Mach, but still. I can't really recall which geometry I inputted here, but still, you can get the feeling of the distribution of each of these equations I just presented to you, which are going to be the most important. So, as you can see here, this is the total drag. The black one is the total drag, and this is the total drag when it's powered. So it's way lower when it's powered. It's maybe 0.05, which is a lot. So you can see the drag is always between 0.25 to 0.4. Again, I can't recall what geometry we had here. Maybe we have really, really high sweep angles or something, because this looks pretty low drag. But yeah, you can get a feeling that there's a big jump. See here, this is the body base unpowered. This is this red line. Body base powered. Look at that. That's really all the change comes from here. Obviously, because that's the only thing that changes from powered and unpowered. So it's literally like half. Again, can't recall the boat tail and the exit area, but it is gonna reduce it a lot. And then you can see here, well, body wave. It appears lower Mach than 1. Fuck. I don't know why right now. I'd have to look into that. Oh well. You can see that the fin wave drag, I guess I put really low tip angle and high sweep because it's tiny, but this can go, the fin wave drag can go up a lot if you don't properly design your fins right. And yeah, nice graph. So guys, with this video we've actually finished all the aerodynamic modeling I'm gonna cover in this video series. There are some stuff I haven't covered. I haven't covered all the roll part, but I told you you could check Open Rocket For all these expressions, OpenRocket would be the first place I'd go if you want more detailed expressions. Still, I mean, I'm not sure how relevant is that going to be, because you already have so many variables that are very unpredictable. Wind, the thrust, I mean, there's always going to be a better expression, but I think these are good enough, at least to start with. Because wind is going to cause a large uncertainty, and if you have a large uncertainty, well, why go into a higher precision with this, which is already a simplification. And with thrust the same. The thrust, you're gonna get a lot of unknowns there. But yeah, we finished all the aerodynamic modeling I'm gonna cover. So we've covered all the modeling of the normal force in the aerodynamic center, thus the corrective moment on the previous section, and we've just done drag. So you can see drag is way easier. Just not much more to see in drag. You can play around with the variables to see how everything affects. It's really easy to do. So again, I'll just leave it up to you. And that's about it.